Hello and welcome to the 32nd lecture in this series. So last time towards the end of the lecture I had started talking about Lie groups. So let's continue with that. So Lie groups are essentially manifolds which have a group structure such that the group operations, group multiplication and inversion are smooth maps. So and we saw that GLNR is a Lie group, and because these the orthogonal group and SLNR are submanifolds of GLNR, the fact that multiplication on GLNR is smooth will immediately imply that there is corresponding operations on these groups are smooth as well. So these are also Lie groups. Now in the context of vector fields, there is a special class of vector fields on a Lie group. So let's define that. To begin with, let us consider definition. We take a group element G, small g. Corresponding to this, I define left translation by G is the map LG from G to G given by LG of x is just Gx for all x in G. Similarly, RG, the right translation by G. The first thing to note is that LG and RG are diffeomorphisms of G. And this is clear because LG, for instance, first let's observe that consider it's the proof for RG is the same as proof for LG. So consider just left translations. Well, we have to check to say that it's a diffeomorphism. We have to check that LG is smooth, bijective, and the inverse is smooth as well. First of all, it's immediate that LG is bijective since we can immediately write down an inverse for this. LG inverse is just LG inverse. So in other words, if I do LG composed with LG inverse acting on X, I get by definition G of LG inverse X, which is the same as G multiplied by LG inverse multiplied by G, which is the same as this, and which is X. Similarly, the other composition is also X. So this the fact that we are able to explicitly construct a inverse map shows that it's bijective. Now as for smoothness, we would proceed as follows. We know that G cross G to G, the map xy going to xy, this is smooth by the definition of a Lie group. So the set G cross G contained in G cross G is a submanifold. This is a more general fact about product manifolds. We had seen it earlier. In any case, let me just mention it again. More generally, in a product manifold, M cross N, the subsets M cross N and M cross N are submanifolds. These are what we call slices for any M n M, little n n, capital N. So the point is that it's quite straightforward to write a slice chart for this these two sets inside M cross N. Now with this in hand, since this is a submanifold, therefore the restriction of this, so let's give this a name, this map as phi, the multiplication map. The restriction of phi to G cross G is smooth, but this restriction is, i.e. the map, the first coordinate has been fixed to be G, so the map is G cross G to G, and this map is Gx going to G times X is smooth. Then all we have to do is observe that finally, actually we are interested in just G, not this small g cross G, but that's the same as G. Finally note that G to G cross G given by G going to, well, not G, let's take X going to G cross X is smooth. This we had seen earlier. This just embeds or rather sort of places G in G cross G as a slice. So given by this is smooth. So let's call this IG. Therefore G to G given by X going to Gx. So this is what this is our left translation map, is LG equals, well, first I start with G, I put it inside G cross G by IG, then I do this phi. Both of these are smooth, so therefore this is smooth as well. So in short, this map is smooth, and so we were trying to check that LG is a diffeomorphism. Bijectivity was immediate because we could construct an inverse, and I just shown the smoothness of LG, and this is true for any G. And so I might as well start with G inverse. LG inverse is smooth as well. So the inverse map is also smooth. So, and the same considerations apply to RG. Now let us say that, so the second definition I need is if I start with a vector field, smooth vector field on G, I should change this more to look like chi x, a vector field x on G is said to be left invariant if what I can do is I can start with the value of the vector field at the identity element. So here E equal to identity of G. So I start with the identity element, then I look at the derivative of the left translation LG at identity. Now this is, in general, this will give me a vector. So this is a tangent vector at identity. XE is a tangent vector at identity. So when I do this, it will give me a tangent vector at G times LG acting on E. But LG acting on E is just G. So this will give me this. In general, this would be a tangent element of the tangent space at LG of E of G, and LG of E is just G itself. So this will give me a tangent vector and at the point G. Now the condition that the vector field is left invariant is that this tangent vector is precisely the value of the vector field at G. So this is what this is the defining property of a left invariant vector field. And as a remark, this is equivalent to the following condition. I can start with, instead of starting at the tangent vector at identity, or rather the value of the vector field at identity, I can start with the at any point. So let's see, let's take x at some point P. Let's apply left translation by G. So the derivative at the point P. And what we want to say is that the condition is that this should be GP. Well, this is what I wrote looks slightly more general than the defining property of left invariance, because if I take this P here to be the identity element, then I have the original definition of left invariant. But here I am demanding it for any P. But it's quite easy to see that this more general thing follows from this. I'll just quickly sketch this. So as I said, this condition is more general than the original condition. So if I want to show that this is equivalent, let me start with the original condition and show this more general condition. So suppose X is left invariant as in the original definition. I want to check this thing here. So let me just plug XP here. Now, according to the original condition, X at any point is given by this, the left hand side here. So let me use that. So this would be DLGP, and then instead of XP I plug in this DLG, rather D, not LG, LP at E acting on XE. And well, now so it's essentially a composition of two maps, two derivatives, DLG P composed with DLP E of acting on XE. Now let's just apply chain rule. According to the chain rule, so I have two maps here. The first map is LP, the second map is LG, left translation by G. So according to the chain rule, and I'm evaluating the derivative of the, if I evaluate the derivative of the composition, the first thing, well, LG composed with LP at identity, chain rule would tell me that this is the same as DLG of at the point LP of E, which is just P, composed with DLP at E, which is exactly what I have here. So what I have here and what I have here are the same. So I can just write this as DLG composed with LP at identity acting on XE. And finally, you just note that LG left translation by P, then you compose with left translation by G is the same thing as, so here I'll make LG composed with LP is the same as LGP. So DLGP at E of XE. Again, going back to the definition, original definition of left translation. So if I had a G here, it would be G would occur here, but here I have a GP. So what I get is XGP, which is what we wanted. So I get this equation here, starting with this one. Right. So now, so this is the definition of a left invariant vector field. Then we also observe that the set of left invariant vector fields on G forms a vector space over R, and we denote it by this Gothic G. Now, right, the fact that it's a vector space, if we add two left invariant vector fields, So it's immediate just because left translate the derivative of any smooth map is a linear map. So if I start with two left invariant vector fields, if I add them up, it's immediately clear that this equation here is will continue to hold for the sum. Similarly, if I take a multiplied by a fixed real number, a vector field, left invariant vector field by a fixed real number, the new vector field will also satisfy this. So we get a vector space. Now, even though, as I remarked earlier, in the last lecture I had remarked that the set of all vector fields on a smooth manifold is not a finite dimensional vector space. However, and the same thing holds true on a Lie group as well, that if one looks at the set of all vector fields, it's certainly not finite dimensional. But this left invariant vector fields form a finite dimensional vector space, and in fact our claim is that the map from the tangent space at identity to G, let's call this map again as some phi given by, actually I want it the other way. From G to the tangent space at identity given by phi of x. I start, so this G on the left side consists of left invariant vector field. So I start, the input is a left invariant vector field and I just evaluate it at the identity. That's this map. So this map is a linear isomorphism. In particular, the dimension of the set of left invariant vector fields, space of left invariant vector fields, is the same as the dimension of the tangent space at identity, which is the same as the dimension of G. So let's prove this. So first thing is, I said that it's a linear isomorphism. So the first thing is that linearity is clear. Since if I add if I consider x1 plus x2, I'll be looking at the value of x1 plus x2 at identity, which is the same as the value of x1 at identity plus the value of x2 at identity. Linearity is clear, and so what we have to do is check that the map is bijective. So since it's linear, we just have to check that the kernel is just the zero element. So suppose phi x is equal to 0, then xe would be 0 since phi x is xe. Since x is left invariant, x at any point G is dlg of xe. This would also be 0 for all G. So this proves that only the zero vector field, which is also trivially left invariant, is the only one which gets mapped to 0, the zero tangent vector under this map. Now as for surjectivity, so this proves that hence phi is injective for surjectivity. Let V be an arbitrary element of TEG. So I would like to realize V as the value of a left invariant vector field at identity. So I do the expected obvious thing, which is, let's go back to the definition of a left invariant vector field. What in effect it's saying is that if I know the value of the vector field at identity, I know it at any other point xg. So if I know this, I know xg, and they are related by this equation here. So now we can turn this around, and suppose we are given some tangent vector at identity. I'll use this equation to define the vector field at any point g. So define a vector field x on g by x at, when I want to define a vector field, I just have to specify what its value is at any point. So in other words, what tangent vector I get at any point. So here I am saying that xg is by definition dlg e of this vector v that we started with. Right. So now this is by definition left invariant. So this x is by definition left invariant. But what is missing is, I have to, when I said that, I said define a vector field x. According to our definition of a vector field, it should be smooth, an assignment which is smooth. Here I just given an assignment which is left invariant. Smoothness of x, it's not immediately clear, because the problem is that we are varying its smoothness with respect to the point g. As g varies, this left translation maps also change, and of course the derivatives change and so on. So but we are what in effect what we are doing is, we are considering the action of the family of maps, family of derivatives on a fixed vector v. So it requires some work to prove this. So I'll come back to this later on. For now, let us assume that smoothness of x, we'll prove it, return to it later. So given the smoothness, the proof is complete, that I have a bijection from the set of linear isomorphism from the set of this to the tangent space at identity. So the significance of left invariant vector fields at this stage is not so clear, but as it turns out, the algebraic properties of the group are entirely reflected in, are entirely captured by the Lie algebra of oh, by the way, yeah, I forgot to mention that this G is called the Lie algebra of G. Now so far G is just a vector space, but it has a crucial additional algebraic operation on it called the Lie bracket, which I will talk about shortly. Then the statement is that this Lie algebra with this additional Lie bracket structure entirely captures the algebraic properties of G, and this statement can be made precise, though I will not be able to prove anything. I will be able to state the precise relation between the algebraic properties of this G, small g and big G. Okay, so now as examples, of course, for GLNR, GLNR is an open subset of MNR, which is a vector space of dimension n squared, and therefore the tangent space at identity, for that matter the tangent space at any point, can be identified with the ambient vector space, which is MNR. When we come to ONR, we have seen that the tangent space at identity is set of space of skew symmetric matrices, and this is usually denoted by SO, little SONR. And the final thing that I'll mention is, we have also seen that the tangent space of SLNR at identity is the space of matrices with trace 0, and this is denoted by little SLNR. So we'll stop here. In the next lecture, I'll talk a bit about the relation of vector fields, ordinary differential equations, integral curves, and flows. So thank you.